Hello, everybody. Thank you for joining us today. My name is Ronaldo Pinto. I'm the Technical Sales Director for AFT, and I'll be hosting today's webinar. Today, we'll be talking about AFT new application for pulsation frequency calculations, which is called PFA, and it's a module of AFT Impulse. If you have any questions during the webinar, you can type it in the chat box of GoToMeeting, and after we finish our webinar, we have a question and answer sessions where I'll be answering your questions. So today's agenda, we'll be talking, as I said, we'll have a brief introduction. We'll be talking about natural frequency and resonance, pipe and system vibration and resonance, PD pump pulsations. Why should we use PFA module? An overview of PFA module. We'll be working on an example. And then we'll be having a final session of how to use PFA in a real case in a pulsation control, solving a field vibration problem. And as I said, we're going to have a question and answer session after we finish the webinar. So, acoustical frequency analysis has always been a very well kept secret by specialized companies, and PFA will give AFT Impulse user a comprehensive access to this technology. PFA is really easy to use, and once you, if you are familiar with the theory of acoustical analysis, it will be pretty straightforward, the application and use of PFA. So potential users that might be interested in a new tool is operators of plants which have a lot of they can have problems on the field with pulsation resonance, consultant companies which might be interested in extending their services to the customers, refineries that the same as operators might have problems with pulsation vibration, predictive and preventive maintenance departments that is usually they deal with this type of application, and also AFT Impulse users that might be interested in exploring this field. So natural frequency and resonance. Every physical system has more than one natural frequency at which it tends to vibrate or oscillates. This is very important, the word tends, because we'll be seeing a lot of a natural frequency. That does not mean they show up in the system. It means that they tend to vibrate if they're excited properly by the excitation forces. So it is possible to excite one of the natural frequency of the system. When that happens, the system will experience resonance. In this situation, the system vibration oscillation will be amplified and grow larger over time. To excite a natural frequency, an external energy source is required. As I said, you will be seeing PFA calculating several natural frequencies. That doesn't mean the system is vibrating at that frequency, but if the excitation, external excitation properly applies to one of the natural frequencies, then we'll have acoustic resonance. In case of resonance, if the energy source is powerful enough or the system weak enough in a particular matter, the system can exhibit fatigue or excessive plastic deformation. Even if the system does not exhibit fatigue, regular excitation over time of a natural frequency can weaken the system or cause the system to perform in an acceptable way. That would be the case of the control valves, that if too much vibration is applied, it is not possible to them to operate properly. In mechanical systems, engineers address such issues as changing the stiffness of the system or changing the mass of the system. Piping systems can vibrate or resonate in two ways. Through the pipe solid material, this is called mechanical vibration. If the vibration frequency is at the natural frequency of the system, it is called mechanical resonance. Through the fluid inside the pipe, this is called acoustical vibration. If the vibration frequency is at the natural frequency, it is called acoustical resonance. So we have two types of resonance: mechanical resonance and acoustical resonance. And this is what PFA will help you differentiate, because it is important to determine whether it's a mechanical problem or acoustical problem, because the solutions to the vibration problem depend on the nature of the vibration. There are many causes of vibration resonance in a piping system. And a common cause of acoustical vibration or resonance is caused by positive displacement pumps, known as PD pump. PD pump cause pressure and flow pulsation in the system. This pulsation can excite any of the natural frequency of the fluid and result in acoustical frequency. It is important to say that this is not the only source for acoustical resonance. It can be other sources. So again, the PD pumps might not be the only cause. Another things would be also centrifugal pumps can cause acoustical frequency, acoustical excitations, and it is important to determine whether or not it's being caused or not. Acoustical resonance is a concern because it can cause piping vibration, cause the piping system to vibrate excessively. This can manage the piping, the joints, and the pipe supports over time, disrupt the quality of the production process, lead to frequent maintenance, which is costly in terms of labor, materials, and lost production. So why should we use PFA module? PFA module allows users to predict and understand resonant frequency so they can be avoided in operation. Most of the time when you do a layout of a pipe, of a system driven by PD pumps, you have to place the supports at certain distances. And one of the things you have to predict is the natural frequencies to avoid the coincidence with acoustical frequencies. So PFA will help you do that. Calculate forces generated by pressure pulsation. And this is very important if you want to do a fatigue analysis and comply with B313. Automatically create scenarios to evaluate the amplitude of the pressure pulsations and magnitude of forces when operating in resonance with any of the acoustical frequencies. So the standard 670 API 674 establishes limited for the magnitude of the vibration, and you can create scenarios and see if your system operates at that frequency, whether or not it will comply with 674 standard. So let's start with PSA process and impulse and see how it helps you calculate the natural frequencies. So step one, you have to turn on the pulsation and frequency analysis module. Step two, strike ring the system. Step three, calculate acoustical frequencies and select the frequencies and pump RPMs of interest. Create a PFA specific scenario representing the PD pump. So let's start in detail with step one. Turn on the pulsation frequency analysis module. Select the PFA module will not be active by default. If you want to use it, you need to activate it. So first you have to select and activate the modules from the tools menu and check the PFA pulsation frequency analysis. After that, you have to go up in the analysis tab and select the pulsation analysis from the analysis module and check use. This will change the items of the analysis module and you'll have a new set of setting that is called new pulsations menu item. So let's look into it. So the first step is to activate it. So to activate it, you come in here in this little box, and you make sure that PFA pulsation is activated. Once you do that, it won't be able to use. So then you go to analysis tool, and you say pulsation analysis, and you say use. Once you do that, then a new menu will be available, which is the pulsation setup. So the second step will be to build a model. So we're going to be working with the model example. This model represents the suction side of the system with two PD pumps, J8 and J9, in parallel, fed by a centrifugal pump, G1. So we will be analyzing PD pump J8. So what is the system we're going to work with? So we have two PD pumps here, J8 and J9, and we will be applying the force to J8, and we have a centrifugal pump supplying the suction of these two PD pumps. So step 2, ring the system. When we say ring the system, it's also called hitting the system. A common test for mechanical vibration and natural frequency measurement consists in striking the pipes with a short hammer blow. This hammer has the head of the looks like a sledgehammer, and the head is made of rubber. So you cannot hit it too hard. It has to have an ideal impact. So an ideal impact is a perfect impulse which has an infinitely small duration, causing a constant amplitude of the frequency domain. This will result in all the modes of vibration being excited by the equal energy. So again, if you want to determine, my screen's not being displayed. Okay, now let me see. Okay, thank you. It looks like my screen has been displayed, so sorry for that. Now I activate it. Thank you for your message. Okay. So in step 2, we're going to ring the system. A common test for mechanical vibration and natural frequency measurements consists in striking the pipes with a short hammer blow. An ideal impact is a perfect impulse, which has an infinite small duration, causing a constant amplitude in the frequency domain. This would result in all the modes of vibration being excited with equal energy. So again, you cannot hit it too hard. You cannot hit it too soft. So it has to be an ideal impact. With PFA simulation, we will replicate this test in a digital mode. We will strike or ring the system with a very short pulse or a sudden increase in the flow rate. This is our computational hammer. We will observe the natural frequency of the system. So we will simulate the test of mechanical vibration in PFA to determine the internal acoustical frequencies of the system. So continuing with step 2, we select the pulsation setup for the analysis tool, this is where the ring will be defined. You have to say where you're going to hit the system. Specify the junction. Only one in the system can be specified, and pulse start time. The automatic magnitude of the strike will be twice the steady state flow. So first part is we're in this pulsation setup menu, and we're going to specify where we're going to apply it. As I said, we're going to apply it in junction 8, and the system will automatically calculate it for you twice the steady state flow. And if you want to specify yourself, you would check on this. Again, the strike has to be ideal. It cannot be too hard. It cannot be too soft. And that is why we provide an automatic calculation of the strike. So it will be properly to excite all the acoustical frequencies. Then in the same menu, the pulsation source is defined here. So here we're going to specify the pulsation source. It is a PD pump. Then the pump characteristics are entered, and the pulsation setup tab, and the PD pump setting lab. So the next step is to specify the pulsation source. It's a positive displacement pump, 5 heads, pump speed 250 RPMs, and speed buffer of 12%. If you just want to examine the acoustical natural frequencies, and they're not necessarily caused by PD pumps, you will select others in this case instead of positive displacement PD pumps. So the next step would be generally all the pulsation, the PD pumps or have a pulsation bottle that acts as a low pass filter. So you want to model that and analyze only the low frequencies. And so this is what this part of the menu is for. The square pulse will excite higher frequencies that we care about. A low pass filter will remove these unwanted higher frequencies. And generally this is done because if you have in the system high frequencies, that is very difficult to handle. So what you do is you use bottles to filter them and handle the low frequencies, lower frequency below certain hertz. Generally it's 100 hertz. In this case it's 140 hertz. And because these are low frequency, low energy, and that means that they can be easily excited, and you can handle them. Not being the case for higher frequency. So this is the section. Here's a modeling of the low pass filter. Is a Chevy-Chev system, and it calculates automatically from the pump you specify the cutoff frequencies that it will filter for you in the system. Finally, we have in the other tab, in the PD pump setting, you specify all the details of the pump. So here, in this case, we have 120 RPM, bore 40 millimeters, stroke 75 millimeters, rod length 360, and so on. So here you specify all the details of the PD pump. So now the pipes as sections after the pulsation setup is defined. This is done by impulse, the same as any normal transient analysis done by impulse. The pulse cutoff frequency will determine a maximum step in the minimum number of sections of the controlling pipes. Some pipes can be excluded from the analysis, and the reason for this is not that not all the elements in the model are pipes. So in this case, P2, P8, and P9 are volume elements, and they're not real pipes. So this the bottles, so you don't have to include them in analysis. And also P10 is acoustically isolated by the centrifugal pump. So you have these pipes are the bottles, so you don't need to analyze them. And this pipe, P10, is isolated by the centrifugal pump. So this pipe here does not need to be included because the system that you're interested in is the suction, and you don't want to include this pipe in the system. So how do you do that? Once you have the pipe sectioning, you come in here and you have a checkbox. And here we're excluding pipe 2 by unselecting in the checkbox. And also, we unselect pipe 8, 9, and 10 by unselecting in the checkbox. With everything defined, we can view the flow pulse that will be used to ring the system. So click in pulsation graph in the lower left corner. So in the left, in the sectioning pipe, you will select this show pulsation graph, and it will show you the strike that is going to be applied in junction 8. So here's the strike, and as we see, it's a very short time strike. So you have several options to see it. The pulse itself, the fast Fourier transform, which shows it in the frequency domain. Then we have a low pass filter pulse for the fast Fourier transform, and the fast Fourier transform with the low pass filter applied. So here we don't have the low pass filter applied, and here we have it, and as you can see, it is filtered at 140 hertz that the system calculated automatically for us. When you hit OK, is click on the section and pipes window, the filter ring will be applied on the junction representing the PD pump. So it will be applied on junction number 8, here is a pulse, the strike that we're going to be hitting it with. So let's review it in the AFT Impulse a little bit. So again, what we do first, here we have the system, we have the centrifugal pumps. This is the PD pumps where we're going to apply it. So we go to the analysis, we go to pulsation setup, and here we first specify where we're going to apply the we're going to strike the system, which is junction 8, and the system will be applied in 1 second, start time in 1 second, and it will be automatic calculated by PFA. So, and then we specify the pulsation source. We said that it was a positive displacement pipe, number of heads 5, 250 RPMs, and buffer of 12. And finally, we have the low pass filter that is calculated for us. So not all the high frequencies will not be analyzed, and it sets the 140 hertz that is established based on the pulsation source that we defined. And finally, we go to the tab with the PD pump settings, and here we specify all the characteristics of the pulsation setting of the PD pump. It's going to be operating at 120 RPMs, and all the physical, the bore, the stroke, the raw length, the clearance, the suction pressure. So he can calculate the pulsation that is going to be applied when we model the system to check it with API 674. So once we do this, we come to analysis tool and we go to the sectioning. So we will section the pipe based on the frequency cutoff. And finally, we determine if we unselect those pipes that we don't want to be included in the system. As we said, pipe 2 is a bottle, so it's not really a pipe. And also, pipe 8, pipe 9, and pipe 10 are pipe 8 and pipe 9 are bottles, so we don't want to include it in the analysis. And pipe 10 is isolated acoustically by the centrifugal pump, so we also want to exclude it. So now we hit a pulsation graph, and this is will show us the strike of the system. So we have the pulse itself, then we have the fast Fourier transformer in the frequency domain. We have the low pass filter pulse, and we have the fast Fourier transform and the low pass filter, which filters it at 404 RPM hertz, which is determined by this by PFA. So when we hit OK in the system, it tells us that PFA module will now place a forcing function onto the junction 8 that we selected. And when we say OK, if we go to the junction A, we see a T of transient. If we open it, we can see the transient in junction 8 and show the graph. Here we have this, the ring or the strike we apply it and this junction to determine the acoustical frequency of the system. So now after running the model, we go to the graph results window, select the new frequency tab, select the pipe location to analyze, and click to generate. You can select more than one location to see the acoustical frequency of the system. The spikes show the frequency that excite the system in the location. So here, once we run the system, we go to the frequency tab and we select the pipes we want to see the frequency of. Like here, we selected pipe 4, pipe 5, and pipe 6. And here we have all the natural frequency. It is important that this, the magnitude or this point, this doesn't mean this little frequency that shows here is more important, is not as important as this one, because all of these frequency can be excited. So these peaks that you see here, although they show a high level and a low level in the graph, if the frequency is excited, they can magnify the amplitude. So the magnitude of the peak does not determine whether or not the frequencies can be critical for the system. It only depends on the nature of the frequency. So once we do that, we select the range of frequency with the largest pressure, and left click and hold while dragging the mouse cursor, or the range selector will appear on the graph. The range selector will determine the maximum value inside of the selection. When the mouse button is released, the frequencies where the maximum pressure magnitude is located out using the annotation. So you drag and you select the frequency you're interested in, and then you can create a scenario for each frequency to analyze whether or not if the system complies with the API 74. So here in this case, we selected 34 hertz. and you can say evaluate the excitation frequency. And once you do this, it will put a dot, a red dot, and it will create in a scenario for you, and you select here what RPMs you're going to operate at. So if we go here to the it created a scenario for the PD pumps to operate and at resonance and RPMs, and you say, okay, either if you select one of these, it will deselect it, and it will not create the scenarios. So the table shows which pumps RPMs will be used to create a childless scenario. Click the RPM values to select or deselect. The italicized values are deselected. Creating a scenario based pump speeds. Check yes on the confirmation dialog. This will automatically create the PFA scenarios. So once here, it will create the scenarios. And so let's move on to the program and show you how it works. So after you finish step 1, step 2, you run the program. So now it's calculating the acoustical natural frequencies of the system. And again, it was strike right here in this junction that we specify. So we go to the output, we go to graph results. So here we have a tab that is called frequency. In this tab, we select the pipes we're interested in. So you can select any of the pipes. I'm going to select pipe 4, pipe 5, pipe 6, and pipe 7. And I'll tell it to generate it. So here we have all the natural frequency. If you want to see only pipe 4, you can deselect it or select them all. And then we have all the frequencies here. So if you drag and create a square, it will tell you the frequencies you are at. And if you want to examine if the pump operates at that frequency, because either you measure it in the field or you are interested in it, so you will right click it and create an evaluation excitation frequency. If you go to the lower one and I say evaluate, it will give me a message. And it will tell you that this frequency has no excitation pump speed, and that's because the RPMs you define. So this frequency will not be affected by the system. So it's a frequency you do not need to worry about, and it will give you a message. So if I select this frequency and I say, okay, create a scenario, evaluate the frequency, we have a red dot here created for us, and now it tells us the frequencies that it will create scenarios for the pump to operate at. So in RPMs, 250, 166, and 125 RPMs. So maybe you're not interested because you know your pump is not going to operate at 125, but it can possibly operate in 250 and 166. So I'll deselect this one and then say, okay, create these scenarios. So it gives me a message. It will create two child pump scenarios with flow rates at 162, 66, and 250. And you see that 125 is not showing because I deselected. So now, if I go to the work page, now I see the scenarios checked, and I say, okay, let me check if I operate my pump at 166 RPM, will it comply with API 674 code? So I go to this scenario. I select this. Okay, so now I go to this scenario, 166. And now, if I see if I open this tab, and I go to the transient, you will see that with the characteristic of the pump, it created an excitation that's properly for the pump. So now this is the pump head created by the pump, and it was created by the program using all the physical characteristic of the pump that you gave when you said pulsation setup of the pump, when you gave it the characteristic. So it is important to remind you that this is a read-only scenario. You cannot edit it. It is created to see if it complies with the 674. So now if I run it, it is analyzing the system operating at 160. If I operate the pumps in 166 RPM, so if I go to the output and I go to pulsation summary, it will give me, say, checking AFT API 674 pulsation pressure limits, pulsation peak-to-peak pressure within the allowables. So the peak-to-peak pressure occurred in pipe 8, station 1. The maximum allowable for the API is 188 psi. Vapor pressure margins are within the allowable levels. So as I said, this would be step 4. The table we went through in the program, the table showed the pump's RPM, so it created a scenario. Here are the scenarios created automatically for you to check the RPM if we operate the system at that pump, at that RPMs. They are read-only, so most of the model cannot be changed. They will be deleted when the parent is changed. So when you change the parent, you make any change, you have to go through the process again and create the system to check whether or not the system. And the reason for that is generally any change will change the acoustical frequency of this natural frequency of the system. So you have to check again whether or not it complies with the code. They are named with the pump speed frequency as we saw. So the junction where the ring was placed is updated to be flow versus time profile of the pump. And we saw this when we saw the transient. This is based on the number of pump heads that was specified when you define the PD pump in the system. We ran the model and we checked the excitation frequency, and this is basically what we did. At the end of the run, as we saw, the maximum peak-to-peak pressure levels are checked against API 674 standard. If the levels are okay, you will receive an okay confirmation. In the case that it does not comply, and warning is given if there are locations which exceed the maximum set up by the standard. It will list the location where the largest deep differential pressure occur, and it will tell you where it's not compliant with. So now let's work a little bit with pulsation control. So let's say you have a field problem that you're trying to solve. So now let's see how PFA comes into play and how it combined with the pipe stress program, it can help you solve a problem and determine whether or not it's a pulsation, acoustical problem or a mechanical problem. So step one, the first, if you have a field problem, you measure in the field the vibration. So this is the result of the vibration problem. And here are the frequency excited: 16 hertz, 33 hertz, 49 hertz, 66 hertz, 83 hertz, and 97 hertz. So now you want to determine whether or not each one of these frequencies that you're seeing high pulsations are mechanical or acoustical, to determine what solution you will apply. So if you have acoustical resonance or mechanical resonance. So now you would create the model in the system. What do we have here? We have PD pump. We have a PD pump discharge that is feeding a tank. And we're seeing problems of high vibration in these two pipes, pipe 22 and pipe 12. So this is where we measure the frequencies that we did to determine the type of solution that we're going to apply. So first you create the model in Impulse. And then in the step two, you calculate the acoustical frequency following the steps described at the beginning of the webinar. And here we see that we see the frequency 16 hertz, 33 hertz that we measure in the field, 50 hertz that is and 92, 99. So now that you calculated the acoustical frequencies, you also do it for pipe 22 that you're also observing problems in the field. So now you also see 16 hertz, 33 hertz, 49 hertz, and 99 hertz. So conclusions in the acoustical calculation: vibrations peak at 16 hertz, 33 hertz, 49 hertz, 66 hertz, and 99 hertz most probably is due to high shaking forces as a result of a near acoustical resonant condition. Vibration 83, which we didn't observe in the acoustical calculation frequency, must be a result of mechanical resonance or high pulsation forces without resonance, which is a non-properly compressor bottle sizing problem. So now we come to step three. So we calculate the mechanical frequencies using pipe stress programs. In this case, I use Caesar. So I built a model in Caesar, and I did a model analysis. So now, in the model analysis, we calculate the natural mechanical frequencies. And we see 33 hertz, 48 hertz, 84 hertz, and 99 hertz, 98.59 hertz. So now that we calculated the frequency, we come to a conclusion. High vibration peak in 83 hertz most probably is caused by a mechanical nature. High frequency at 16 hertz is probably is of a acoustical nature because it was not observed. And vibration peaks 33 hertz, 49 hertz, 66 hertz, and 99 hertz are both mechanical and acoustical nature. So in this case, we have acoustical vibration resonance matched with acoustical mechanical resonance. Conclusion: pipe and vibration problem in many cases are a mixed nature, part mechanical and part acoustical. Each category requires a different solution approach. Not all vibration problems can be solved by mechanical measures. So this is very important, this last statement. Not all mechanical vibration problems can be solved by mechanical measures. So changes the supports in the system when you have an internal acoustical resonance will not solve the problem. You will have the high vibration, the high forces, because the problem is caused internally. So in this case, this is why PFA is so important, because you have to determine whether the problem is acoustical or mechanical. Solutions. What solutions can you apply? So if it's an acoustical problem, frequently advised modifications are installation of RFS plate, increasing the diameter of the pipe parts, relocating closed valves, or installation of additional volumes. If it's a mechanical problem, frequently advised modification is the installation of additional supports, relocating or improving quality of supports, or by increasing the stiffness of the structure of the system it's mounted. Like sometimes you might be using supports that are too flexible and they're easily excited, so they don't, if they're too flexible, or like if you're using if they're too flexible, they're not an effective dynamic restraint. So the system will vibrate. So you might want to increase the stiffness of the support to assure that it constitutes a dynamic restraint. In case that none of these acoustical or mechanical problems are detected, in the case of no matching frequencies were found with those measured in the field, either mechanical or acoustical, the next step to look for a solution would be to look into the pump bottle sizing. It might be the pump bottle sizing is not properly done, so you might want to check this the size of the bottle, because it might not be filtering or working properly as it was intended in the initial design. So there's some things that you have to know. The acoustical model that PFA are very precise. Accuracy of prediction of acoustical natural frequency is relatively large. The error margin is small, between more or less plus or minus 5%. And the reason for that is because errors control limited parameters like the geometry, the speed of sound, and the compressor RPM. In the case of the mechanical model that we built with Caesar, accuracy of prediction of acoustical natural frequency is relatively low, and the error margin is between 10 and 20%. And this is due that there are many parameters that you have to take into consideration when you that can cause these error margins, like modeling properly the boundary conditions, modeling the rack structures, support clearance, support lid off, support cycling, support stiffness, friction, nonlinear supports, uncertainty masses. So trust in the model and build to determine the mechanical frequency, you have to give yourself a margin of bigger margin of error between 10 and 20%. So now we move on to the section of questions. Do you have any questions? Well, apparently there's no questions. Thank you for attending the webinar. Appreciate it. This is a very interesting field. If you want to explore it or you have any questions, just shoot me an email. So now what's next? You will receive a follow-up email with the link to today's webinar and also the upcoming webinars. You can download a free demo from your website or request an evaluation license. Pricing information, if you are located in USA, yeah, it's posted in a website. And if you in an international out of use United States, you contact your local dealer channel partner. Thank you again for joining us, and we invite you to our next webinars that will be showing in the next week. Goodbye.